Okay, so here we're going to show you how to do some experiments with flip-flops on the Binary Explorer board, which is lab number 4. So you can download the description from the course website. I'll just move over here. And you can see, for example, we have this lab, flip-flops and registers we'll be talking about. The procedure, there's a separate document for observations that you can use to start your own lab and save a bit of time. So, as normal, what we do is we download the base file. So the lab procedure gives us a reference, 2 different options. So I'll just pick one of these. We go there and we download the file, and we'll unzip it somewhere. So I'll just save it, and again I'll put it on my desktop. There we go. So as we normally have to do, you have to unzip this somewhere. Just put it right here. And then open the Project Navigator file. When you double click on that, this will open the ISC Project Navigator. There we go. And this opens. So now again, you have to make sure you're in implementation mode, and be careful because this file comes with some additional stuff we'll use in later labs, and you still just want to open the I/O connections schematic file. And you can bring that file up, as you can see, and it just looks basically like it always has. So the first thing we're going to do is an RS latch with NOR gates. So this is what we did in class. So we'll place 2 NOR gates. 1, 2. Like say here and here. And then we'll wire up 2 switches to the inputs. So you can get the schematic from the lab manual. And if it doesn't work, sometimes it takes... if you keep getting errors, it helps to zoom in, I find. Let's try this again. And you have to ignore, for some reason the wire doesn't show up on my screen, so you might not be able to see that. And again, we cross-couple the output, so this is where the latch is being built. So we have 2 outputs, and we connect one of them here, and one of them here. Now we're going to be downloading to the physical board, and I'll just pretty it up a little. There we go. So we do that, we save, and you can go over to the design here, and you have to click, again with I/O connections clicked, not anything else. Hit implement design, just double click on that, and it needs to run through until generate programming file is complete. So wherever you unzipped it, once that's complete, as before, we'll program the board just by running the program.bat. So you have to wait until you get that green check mark by generate programming file, and it might take a second depending on how fast your computer is. And there we go. So we let this run, and again it should take 30 or so seconds. If it goes right away, then something's probably wrong. And when it's done, it'll say, please wait. So we just wait for it to complete. And there we go. So it's finished. So we just press any key or just close it. I'll just close it. There we go. So now we've programmed the board. So we have 2 outputs here. The first 2 LEDs. And these 2 outputs here are LED 1 and LED 2. So LED 1 is the Q output and LED 2 is Q complement. So we know it's an RS latch, so one of these inputs is reset and one of them is set. So for example, if I click that one, it does nothing. Click that one, it sets the output. And then it latches it, because when I put the switch back to 0, it's keeping the state. So we can clear the output. So again, this is Q complement, and set the output. So you can sort of figure out which is reset and which is set that way. If you set them both high, this is an invalid state, and we notice that both Q and Q complement go to 0, which is not what we want. So in the lab, just go through, and it gives you an observation table, so you can fill out this table. You have to do a complete lab report for this one, but you can go through that and fill out what happens when you set the switches to cause what output changes. So as an example, this first line here, I say what is the transitions required. If we're already, Q is in state 0, so we need to already be in Q state 0, so play with the switches. And what are two ways, assuming the switches are in 0 state, what are two ways we can keep that state the same? So one of them is obviously if we have switch 1 to 0 and switch 2 to 0. Another one is if switch 1 is 1 and switch 2 is 0. In a similar way, you can see transitions to other states. So if we're in the 1 state and we transition to the 0 state, this is equivalent to resetting the device. So, that occurs because the R input goes high. And you can go through the whole table to get your state transition table. Alright, so now what we're going to do is you can do the same thing, except you can add NAND gates instead. So let's do that. And this will give you another implementation of the RS latch. So again, under logic, we find NAND2. NAND2, there we go. And you can just drop it down right in place. So when you do this, I'll warn you that the outputs or inputs, they may not be the same. Part of the lab is to discover what they are, or you can look up online. Again, every time you change something, you have to rerun implement design, and you need that green check mark by generate programming file. Once you get a green check mark here, you can rerun the program file. So we'll just wait for that to finish, and we'll rerun the program. I won't do part 1C, so part 1C, you wire up a JK flip-flop. So this will be a real flip-flop where we have a clock input. Right now what we're doing is just latches. So you run program. And in the meantime, reopen the schematic. And actually I'll show you briefly the JK so we can delete all that stuff. And you see when the lights go on, it's done here. So again, you can play around with the input. So what you notice right away is that both inputs are on. This is some sort of invalid state. So when the inputs are 1, 0, 0, we're in this invalid state. So what it actually looks like is you can sort of figure out if these inputs are active high or active low. Being that, what is the normal state? Is it stable when both inputs are 1, and then it changes when one of the inputs goes to 0, or how does that compare to when we built it with NOR gates? So this is with NAND gates. The JK flip-flop, the schematic there you can see from the lab manual. So it's a little more complicated, but we can build that. And you notice that I've listed with the schematic what the inputs are. So we can see that this is the J input, this is the K input, and this is the clock. So to build this, we just go through. What do we need? So we need a 3-input AND gate. And we'll put 2 of those down. 2-input NOR gate. So you can see how this is quite a bit faster than using the in discrete logic chip. So we just drop down all the gates we need, and we need a 2-input AND gate with an inverted input. And another 2-input NOR gates. So when you build the RS latch, one way you can describe it is you'll have when you build the JK flip-flop, you can describe it as having 2 RS latches. And you'll actually see this. So what I'm drawing here, that was when we built an RS latch out of NOR gates. This obviously looks very much like that. So there's one of them. Pretty up the wires here. And then there'll be another one over here. So again, we have this same cross-coupled architecture. Oops, auto failed. And again, I'll just drag this wire up to make it a little cleaner. So then you can just go to the schematic and copy this whole thing out, which I'll do here. And here we go. Here we go. So this is the J input, which goes to the top one. This is the K input here. And we have a clock input. So the clock input goes there. And the clock input also goes to these two pins. So we can sort of see when we talked in class about how we build flip-flops from two latches, one with an inverted clock. So you can notice right here, we seem to have a RS latch, these two gates here. And we also formed an RS latch with these two gates. Here, in this middle part, we have the two AND gates on the input. So that is what we showed as an enable pin. And same with the thing here, we have what is effectively an enable pin on the inputs. So you notice the clock, when it's high, will enable these two, and the data will go through to this latch. But you notice the clock, the enable pin for the second part here, has that circle, meaning it's complemented. So what this means is that the enable pin is active low. So when it's high, the data loads through the first part, and then when the clock goes low, it loads through to the second part. So this is sort of how we create a flip-flop from a latch, because it's only right when the clock changes that the data goes through to the output. Anyway, so we finish the design. We connect this input here to the Q complement output, and we connect this to the Q output. I'll just double check, yeah. And finally, we'll wire these to the LEDs. So the top gate is Q, the bottom gate is Q complement. Again, save it, and the normal process, run the design, implement design. So we let that run, it'll take a minute, and again, you just run the program about that. And once this is done, you can again do the same thing. We'll have this table showing that you have to fill out. So it says if the output Q is in state 0 and you want to move it to state 0, what do you have to set the J and K switches to? You have to remember for this part that we actually are dealing with a tiny bit different in that we have a clock input. So you run program.bat, let that go. So when you have a clock input, you'll have to set the inputs to the state you want to test and then clock it once. This was different from the latch where you just set the inputs and that was the change. So you can change the inputs a whole bunch and it doesn't do anything until you hit that clock pulse. So you have to remember we have input J, input K, and input clock. So there we go, it's done programming. So again, Q complement is LED 1 and 2 respectively. And playing around, we can see, for example, when inputs J and K are both high, we expect the output to toggle on every clock pulse, which it does. And you can set the outputs, if they're both 0, it stays the same. So when you're doing the lab, what you have to do is, again, filling out this truth table, going from state 1 to state 0, this table is saying there's two different ways of doing it. So if we're in state 1, so I can put it to state 1, How can we move this to state 0? Well, if the inputs are 1 and 1, it'll move to state 0. But also, if it's j of 1, k of 0, it'll also, or in that case it stays at state 1, sorry. If j is 0, k is 1, then it'll move to state 0. So that shows there's two different ways to achieve the same state transition. So this is part 1 of the lab, is building the flip-flop from discrete gates. Part 2, which we'll have in a second video here, we'll be using registers for a simple counter. So you can look up part 2 if you wish next. I'll just stop recording.